Waves are everywhere. The ripple on a pond, the sound coming out of a speaker, the pulse of alternating current in your walls, even the slow rise and fall of the tides. Beneath almost every wave you have ever seen sits one surprisingly simple picture, a single point going around a circle. That is the promise of this video. By the end you will see exactly how spinning in a circle turns into a smooth, endless wave, and you will understand why two of the most famous curves in all of mathematics, the sine and the cosine, are really just two views of the same rotating point. Let us start with the simplest possible circle. We draw it centered right at the origin, the middle of our screen, and we give it a radius of exactly 1. Because the radius is 1, we call this the unit circle. That single choice will make everything that follows clean and beautiful. Now place a single point on the edge of this circle. We will start it out on the right, sitting on the horizontal axis. Think of it as a tiny bead threaded onto the circle, free to slide around the rim. This bead is the only thing we really need to watch. We connect the center of the circle to this bead with a straight spoke. As the bead moves, this spoke will sweep around like the hand of a clock. Keep your eye on that spoke, because the angle it makes is the master control for everything. Let us set the bead in motion. We will spin it counterclockwise, the direction mathematicians always favor, at a nice steady pace. Watch how the spoke turns and the bead traces out the full round trip, coming back to where it began. Here is the key move. Instead of watching the whole bead at once, we are going to split its motion into two separate questions. First, how high is the bead? And second, how far to the side is it? Two simple measurements, tracked independently. Let us focus on the height first. We measure straight up from the horizontal axis to the bead. When the bead sits on the right at the start, its height is 0 because it is level with the center. Nothing above, nothing below. Now nudge the bead upward along the circle. Its height climbs. As it rises toward the very top of the circle, the height grows all the way up to 1, the full radius. At the top, the bead is as high as it can possibly get. Keep going past the top and the bead starts coming back down the left side. The height shrinks again, back to 0 when the bead reaches the far left. So over the top half of the trip, the height went from 0, up to 1, and back to 0. Now the bead dips below the horizontal axis. Here something new happens. The height becomes negative. We are measuring how far below the center it is. As it swings through the bottom of the circle, the height reaches its lowest point, -1. Finally the bead climbs back up the right side, its height returning to 0 as it arrives home. That is one complete cycle of height, 0, up to 1, back to 0, down to -1, and home again. Simple to say, but watch what it looks like drawn out. To really see the pattern, we need a way to record the height at every instant, not just at 4 checkpoints. So let us build a graph next to the circle. To the right we lay out a horizontal time axis. As the bead spins, time marches steadily forward. Here is how the recording works. At each moment we take the bead's current height and carry it straight across to the right onto the graph. As time ticks forward, the pen on the graph moves rightward, plotting that height. Let us press play and watch the two move together. Watch closely. The bead rises, and the pen climbs. The bead reaches the top, and the pen peaks at 1. The bead falls, and the pen comes back down. Point by point, the height of a point going around a circle is being traced onto the graph. As the bead swings below the axis, the pen dips below the center line too, carving out a smooth valley down to -1. When the bead finishes its loop, look at the shape the pen has drawn. That gentle, rolling curve is the sine wave. Let it keep spinning and the story simply repeats. The bead goes around again, and the pen draws another identical hump and valley. The sine wave rolls on forever, one smooth copy after another, as long as the bead keeps turning. So there is our first big idea, and it is worth pausing on. The sine wave is nothing more mysterious than the height of a point going steadily around a circle, plotted over time. Every peak is the top of the circle, every valley is the bottom. But we promised 2 measurements, not 1. Remember, we also asked how far to the side the bead is. Let us go back and track that horizontal position with the same care we gave the height. Start the bead on the right again. Now its sideways position is at its maximum, a full 1 to the right of center, because it is stretched out as far right as the circle allows. So this measurement begins high, at 1, exactly when the height began at 0. As the bead rises toward the top, it also drifts toward the center line. By the time it reaches the very top, it sits directly above the center, so its sideways position has shrunk all the way to 0, rising up, but sliding inward. Push on to the left side and the sideways position goes negative, meaning the bead is now to the left of center, reaching -1 at the far left. Then dipping to the bottom, it slides back to the center line and the horizontal position returns to 0. Coming up the right side, the bead swings back out to the far right, and the horizontal position climbs back to 1. So this measurement also cycles 1, 0, -1, 0, and back to 1. The very same range as the height, just marching to a different beat. Let us graph this one too, right below the sine wave, sharing the same time axis. This time, instead of carrying the height across, we carry the sideways position down onto the new graph. Same bead, same spin, different measurement. Press play. Notice the pen starts up at 1 this time, because the bead begins stretched to the right. As the bead rises and slides inward, the pen slides down to 0. This curve is already telling a different story from the very first instant. As the bead continues around, the pen carves down into a valley at -1, climbs back through 0, and returns to 1 after a full loop. The result is another smooth, rolling wave. This one we call the cosine wave. Now put the two graphs side by side and really look. The sine and the cosine have the exact same shape, the same smooth rolling form, the same height and depth. If you covered up the labels, you could not tell one curve from the other by its shape alone. The only difference is where they start. The sine begins at 0 and climbs. The cosine begins at 1, already at its peak. It is as if one of them got a head start on the other. That head start is the whole relationship between them. Let us make that head start precise. Slide the cosine wave to the right and watch what happens. Shift it by exactly a quarter of a full cycle, and it lands right on top of the sine wave. They match perfectly. So sine and cosine are not two different animals at all. They are the same wave, one simply shifted from the other by a quarter of a cycle. Mathematicians call that offset a phase shift. Two curves, one shape, separated only by a head start. There is one more knob we can turn, how big the wave is. So far our circle had radius 1, so the wave rose to 1 and fell to -1. What if we make the circle bigger? Spin a bigger circle and the bead swings higher and lower, so the wave grows taller. The bead on a small circle traces a shallow wave. The bead on a large circle traces a towering one. That height of the wave is called the amplitude. So we now have 3 independent dials that shape any wave. The amplitude, set by the size of the circle, the frequency, set by the spinning speed, and the phase, set by where the bead starts. Turn those 3 knobs and you can build an astonishing variety of waves. Let us step back to the circle one final time and appreciate what we have built. A single point, moving at a steady pace around a simple circle, carries within it both the sine and the cosine, the two most fundamental waves in mathematics. The height gives us the sine, the sideways position gives us the cosine. They share one shape because they come from one motion, and they sit a quarter cycle apart because up and sideways are at right angles. That is the entire relationship drawn out in front of you. And here is the thought to carry with you. Whenever you see something that rises and falls in a smooth, repeating rhythm, a sound, a wave of light, a swinging pendulum, a season, you are very likely looking at rotation in disguise. Somewhere, something is going around in a circle. That is the quiet magic of the sine and cosine. Two curves that look complicated on paper turn out to be the simplest thing imaginable, a point patiently going around a circle, watched from 2 directions at once. Keep an eye out and you will start seeing that circle everywhere. If this made it click, subscribe for more visual math.